Welcome to G Fun Facts Online. Today we are stripping away the corporate buzzwords and political slogans to look directly at the thermodynamic and engineering reality of the most ambitious project in human history, the transition to net zero. We hear these terms constantly: carbon neutrality, net zero, the Paris Agreement. But what does it actually mean to rewire the engine of civilization? We are going to explore the physics of the carbon budget, the chemistry of hard-to-abate sectors like steel and cement, the thermodynamics of sucking carbon out of the sky, and the staggering economics of a $178 trillion reality. Let's start with the definitions, because the difference between carbon neutrality and net zero is not a matter of semantics. It is a matter of atmospheric physics. The climate does not respond to good intentions or marketing campaigns. It responds to the cumulative stock of greenhouse gases in the atmosphere. This is what scientists call the carbon budget. It is a finite, specific mass of CO2 that humanity can emit before we breach the 1.5 or 2 degrees Celsius thresholds. Here is where the confusion lies. Carbon neutrality is often used by companies or buildings to say they have balanced their books. They might still be burning fossil fuels, but they are paying someone else to reduce emissions elsewhere, effectively offsetting their pollution. Net zero, however, as defined by the IPCC and the Science Based Targets initiative, is far more rigorous. It requires the abatement of greenhouse gases, not just CO2, but methane, nitrous oxide, and HFCs, to as close to zero as physically possible. We are talking about a reduction of 90 to 95% across all scopes. Under a net zero framework, you cannot just pay someone else to fix your mess. You have to stop polluting almost entirely. Only the final, unavoidable 5 to 10% of residual emissions can be neutralized through high-permanence carbon removals. Why is this distinction so vital? Because of the science of overshoot. Current climate models warn that if we rely on offsets and slow-walk the reduction of actual emissions, we risk exceeding the 1.5-degree limit temporarily. This overshoot pathway is perilous. It risks triggering irreversible tipping points, such as the thawing of permafrost, which releases vast stores of methane, or the collapse of the West Antarctic ice sheet. Once these systems tip, no amount of future carbon removal can put the genie back in the bottle. So if we have to cut 90 to 95% of emissions, we have to look at the sectors that are the hardest to clean up. Electricity is actually the easy part. We have solar, wind, and nuclear. The real challenge lies in the heavy industry sectors, where the problem isn't just energy, but chemistry. Take cement, for example. It is the backbone of modern civilization, but it is responsible for roughly 8% of global emissions. The problem is deep inside the molecular process. To make Portland cement, we take limestone, which is calcium carbonate, and heat it in a kiln. This process is called calcination. When you heat that limestone, it breaks down into clinker, or calcium oxide, which is what we need. But for every molecule of calcium oxide produced, the rock releases a molecule of CO2. It doesn't matter if you heat that kiln with solar panels or coal. The chemical reaction itself releases carbon. Engineers are now working to redesign this Stone Age technology. One solution is clinker substitution, replacing that limestone with calcined clay or industrial fly ash. Even more radical is carbon mineralization. This involves injecting CO2 directly into wet concrete. The gas reacts with calcium ions to form solid calcium carbonate nanominerals. It effectively locks the carbon away forever, while actually strengthening the concrete. We are also seeing catalytic breakthroughs, where scientists are using steel waste as a catalyst to lower the temperature of calcination, turning waste streams into energy sources. Speaking of steel, that is our next heavy hitter. Traditional steelmaking is a dirty business. We take iron ore and throw it in a blast furnace with coke, which is purified coal. The coke strips the oxygen away from the iron ore, but in the process, it creates massive amounts of CO2. The leading scientific alternative is something called hydrogen direct reduced iron, or HDRI. Instead of using coal to strip the oxygen, we use green hydrogen. When hydrogen reacts with the oxygen in the iron ore, the byproduct isn't carbon dioxide, it is just water, H2O. The resulting sponge iron is then melted in an electric arc furnace powered by renewables. The challenge here is thermodynamic. It requires vast amounts of continuous, high-purity hydrogen, which means we need a massive scale-up of electrolyzers. Then there is aviation. This is perhaps the most difficult sector because of the limits of battery physics. Jet fuel is incredibly energy-dense, containing about 43 megajoules of energy per kilogram. The best lithium-ion batteries, they only hold about 0.9 megajoules per kilogram. For long-haul flights, batteries are simply too heavy to get a plane off the ground. The industry is pivoting to sustainable aviation fuels, or SAF. These are liquid fuels chemically identical to kerosene, but made from biological or synthetic sources. We have HEFA fuels, made from waste oils and fats, which are already in use but limited by how much used cooking oil actually exists in the world. The holy grail is power to liquid. This technology combines hydrogen from water electrolysis with CO2 captured directly from the air to synthesize hydrocarbons. It is effectively reverse combustion, turning exhaust back into fuel using renewable energy. And the science shows a double benefit here. Aviation's climate impact is actually double its CO2 footprint due to contrails, those clouds formed by soot and water vapor. SAF's burn cleaner produce less soot and therefore reduce contrail formation. Now, even if we fix cement, steel, and aviation, we cannot eliminate every single gram of emissions. This brings us to negative emissions technologies, or NETs. These are the machines and systems designed to clean up the final mess. Direct air capture, or DAC, is the most technological approach. These are essentially large mechanical trees. Fans pull air across a filter coated with chemical solvents or sorbents. If we use solid sorbents, they act like a sponge, soaking up CO2 until they are saturated, at which point we heat them to release the gas for storage. Liquid solvents are more continuous, passing air through a solution like potassium hydroxide to form a carbonate salt, which is then heated to high temperatures to release the CO2. The problem here is the energy penalty. CO2 in the atmosphere is very dilute, only about 420 parts per million. Concentrating that to 99% purity requires significant energy, roughly 140 to 200 kilowatt-hours per ton of CO2. We also have BECCS bioenergy with carbon capture and storage. This involves growing trees or crops, burning them for energy and capturing the emissions. Since the plants absorbed carbon while growing, capturing the emissions creates a negative loop. The science is sound, but the ecology is risky. Scaling this to a global level could require land areas the size of India, competing with food production and biodiversity. A more permanent solution for storage is carbon mineralization. This is where we turn gas into stone. Projects like CarbFix in Iceland dissolve CO2 in water and inject it into basaltic rock formations deep underground. The CO2 reacts with the calcium and magnesium in the rocks to form solid carbonate minerals like calcite. In pilot projects, 95% of the injected CO2 turned to stone within 2 years. This eliminates the risk of leakage, which is a major concern for traditional gas storage. But technology isn't the only answer. We also have nature-based solutions. The biosphere has been balancing the carbon cycle for millions of years, and we are learning how to leverage that. In agriculture, we are moving toward regenerative practices. Modern tilling turns soil from a sink into a source of carbon. By adopting no-till farming, we allow fungal networks to thrive. Plants exude sugars through their roots to feed soil microbes, which create a sticky substance called glomalin. This glomalin binds soil particles into aggregates, protecting carbon from oxidation and storing it deep underground. Then there is blue carbon, the ocean's secret weapon. Coastal ecosystems like mangroves, seagrasses, and salt marshes are pound for pound more effective than rainforests. Seagrass meadows occupy only 0.2% of the ocean floor, but store 10% of the ocean's buried carbon. Unlike forests, where carbon is stored in biomass that can burn or rot, seagrasses trap carbon in oxygen-free or anoxic sediments. In this environment, the carbon breaks down incredibly slowly, remaining stable for millennia. Mangroves do something similar, their complex root systems trapping sediment to build carbon-rich peat layers several meters deep. Finally, we have to talk about the economics of this transition. For years, net zero was framed as a cost, but new economic modeling has flipped that script. A landmark analysis by Deloitte suggests that the cost of inaction, letting climate change run unchecked, could cost the global economy $178 trillion over the next 50 years. This comes from damaged infrastructure, lost productivity, and health crises. Conversely, a coordinated transition could actually boost the global economy by $43 trillion. To finance this, the world is turning to carbon markets governed by Article 6 of the Paris Agreement. This allows countries to trade mitigation outcomes. Under Article 6.2, countries can engage in bilateral trading. If Norway funds a solar plant in Indonesia, it can count those cuts toward its own target, provided Indonesia doesn't double count them. Article 6.4 establishes a centralized UN marketplace for these credits. The science of verification here is advancing rapidly. We are moving toward digital MRV monitoring, reporting, and verification. We are using satellite radar and LiDAR to measure forest biomass from space, ensuring that a tree protected on paper is actually standing in reality. This prevents the fraud that has plagued carbon markets in the past. In conclusion, the science of carbon neutrality is no longer theoretical. It is an engineering reality. We know how to strip oxygen from iron using hydrogen. We know how to turn CO2 into stone deep underground. We know how to farm in ways that heal the soil, and how to synthesize jet fuel from thin air. The challenge we face now is not one of invention, but of velocity. Net zero by 2050 requires the deployment of these technologies at a speed unprecedented in human history. It requires a just transition to ensure the economic benefits are shared globally. The target is set, the physics is non-negotiable. The rest is now up to us.